Okay, welcome everyone. This is lecture 5.2 on alignment and representation. Today's lecture will talk about, we're extending the concept of alignment and attention, and that will allow us to also start studying one topic I kept telling you about last week, I think, when we look at sentence level embeddings. We'll start studying other methods and other ways of embedding sentences and sequences. One of these approaches that is extremely popular in language, in natural language processing, and is now becoming more and more popular in multimodal as well, is the idea of self-attention. It comes under the name of one specific type of self-attention, which is transformer, and comes with its own particularity, like the idea of multi-head attention and position embeddings. So we will study these. That will also allow us to start studying multimodal contextualized embedding, so like sentence level embedding as an example. And we also will start studying a topic that has been very popular in computer vision maybe since 2011, but really gained a lot of interest in natural language processing in the last 3 years, about pre-training on very large amount of data. And that will be allowing us to also study ideas of multimodal pre-training. So that's our goal for today. So contextualized sequence encoding. So we talk in lecture 4.2, if I remember correctly. No, sorry, 3.2. We talked about sequence encoding. How can we encode a whole sentence in such a way? And here I'm showing a sentence, and how can I encode this sentence? And in this case, I'm going to talk about one type of sequence encoding where my goal is to encode each word by themselves, but with each word being contextualized with the other word. So it's not just word to vec where the word I is encoded, but no, the word I should be encoded in such a way that it takes into consideration the other words, so that if I have the word like plant, I can hopefully disambiguate by looking at the context of it. So that's sequence encoding. There's another type of sequence encoding where maybe you get one embedding for the whole sentence or sequence. And that's also something we'll study now. But how can you do this kind of sequence embedding with the tools we already know how to use? And one of them is bidirectional LSTM. So you could imagine using an LSTM or a recurrent neural network to be able to contextualize one way and then contextualize the other way. And that will give you now a new version of these embeddings that will take better understand, hopefully integrate information from the other words. Elmo is an example, and we had already discussed about it. Elmo and all of these are great, but they are harder to parallelize. If you have a very long sentences, a lot of this computation, to be able to do the embedding of this word, I need to be able to, before that, do all of the other embeddings. And similarly, you need to, that sequential makes things a bit harder. When we want to make things in parallel, you should have a second thing that comes to mind, that comes maybe more from the world of computer vision, is the idea of convolutions. That's the idea of like maybe having multiple kernels, and these multiple kernels could go, and we talk about time-delayed convolution network as a way to be that. And that's nice because now they can be parallelized, because to be able to infer the embedding at this point, I just need to be a local kernel. And that's the same thing with an image. I only needed to do it locally, and that allowed me to process almost the whole image very, very efficiently. But the challenge there is that you need to model. It can be more challenging for the long range, because this embedding will not directly take into unless you have multiple layers. You have multiple layers, then you start having, but by default, the local will mean that you don't have the long range dependency. Otherwise, it requires multiple layers of convolution. And that's what is often used in the CNN, but that brings the computation harder. And one thing also to remember is that these kernels here, although they are trained, as you remember, a kernel is kind of a template. It's looking for a certain type of patterns, and that certain type of pattern will help you determine the response to the kernel. But these are, in a sense, static. Static meaning that they are trained, they learn. They're not hyperparameters, they're still parameters. But at test time, these patterns are the same. So the kernel to analyze these two words was exactly the same kernel that was used to analyze these two words. So the set of kernels is the same for the whole sentence. And so maybe there are other ways we could study that. And yes, self-attention is a nice way for you to contextualize this. It can be parallelized. It allows for long-range dependency, and it can also be the attention weights, which is mostly, you could say, almost the kernel's weights are going to be dynamic as well. So that also allow for more flexibility. They come with a price. The number of parameters can be larger, so that they're not like the perfect solution, but they bring some very great advantage. So I want to discuss about self-attention, and that's what we'll share for the first part of it. Is how can I, and the goal, the formulation of the problem is I have an embedding already for each word. I already have an embedding, but I want to get new embeddings. But these new embeddings, they should take into consideration the other word. So if I wanted to get the embedding for the first word, the word H, here, the first word, I don't want this to just be dependent on the first word, but I want to also know what other words will be useful. And the intuition is I'm going to use attention. So the idea here is that I will have, and I will tell you how I compute those attention in a minute, but I will find a way in such a way that I have an attention telling me for this word I, finding a new embedding for it, how relevant, how important, how similar, how relevant is the second word. And that's what this attention is going to tell me, is like how relevant this is and how relevant this other embedding, the third word. And so I, for the word I, maybe by itself, I like maybe the other words may not change their meaning as much. I mean, the word I will probably have a very differently high attention here, but it may or may not be as important for the others. But for other words like do, like I do not like it, like I do not like, and for the word like, the not, like all of these, the like by itself is the meaning is by itself, if I just embed it, may be very positive. But if I put it in a context, like I do not, like the do not together, the do should really be aware of the not, and that attention should be higher. So at the first step, we're going to go and here the 1,1, the first one means that I'm looking at attention for that first word. And the second one here, and here is a 2, it's a 3, a 4, and a 5, tells me how much should how related are the other words. And so right now I will do the same way I do as an attention or any attention. I take and multiply these, and that will give me my new embedding. And so right now I show you for H1, and let's show it also maybe for for the 2. So in this case, you will have a new set of attentions, and that's really interesting. So now you have a new set of attention. So do and I, is it important? Probably doesn't change so much, but do and not very much. They're very, and maybe like the it probably not as much, but this is different. So I will probably have a very high attention here. That's what the whole, and then I do the same thing as I've done earlier, and then that gives me my embedding. Okay, and so I'm just showing now for all of them just to make it a little bit succinct. But this is the idea of the important aspect. One important aspect of the self-attention is that I'm learning these, and not learning. I'm dynamically computing these attentions that are going to tell me how important the other words are to my words, and then I'm going to use all of these attention to be able to compute these new embedding. So up to now, it looks a lot like the other attention. It's just that instead of having it only one, I have it one for every word. And so that's one difference. But the basic concept is the same. You take the attention weight, multiply by the word embedding, take the attention, multiply the word, and then you do a sum, and that's what gives you the age. But how do I compute those attentions? And that's very that's where it gets a little bit tricky. It takes a little bit of time to get your head around, but like it's worth doing it because then it gets really powerful. So at the first step, I just need to say, although I said it's the same as the input, like these are the same, but for the transformer architecture, okay, up to now, this is called just self-attention. But I need to find a way to compute those attention weight. And then there's many different ways you could do that, but one that is really popular is the transformer way of doing self-attention. And so there, one of the things they decided in the original paper is to say my embedding here of the word, I will project it into a new embedding that's helpful for embedding my H1, but also is going to be helpful to help the others. And that's why this one is useful, is that it's like, it's not just about a new embedding for my H1, it's just not just about reprojecting it, but it's also with the goal eventually to help, how is it going to help the others as well. And then what you do is that you will take the same input and you will project it as what's called, really soon I'm going to call a key and a query, but these are two projections, and you're going to do the same for all of them, okay? And up to now, you're like, hey, why did I do those three connections? Just have a little bit of patience, and I'm going to explain to you. But just for now, take that same input and project it three different ways with those three different matrices. And this, this projection, these cues, I'm going to call them the queries. The keys are the K here, and then the values, okay? So query, keys, and values. And keys and values are usually, all three of them for now are all coming from the same input, okay? And that's why we call it self-attention. We're going to talk about extension where the key, the query and the keys are different, but for now they're the same. So what the beauty is, and how do I get those attention? Because I didn't give you the magic on how to give these attention. The key here, and here's the idea, is I will look at, for this word, that's my query. For this word, which other words are useful? That's what this attention is supposed to tell me. And so what will I do? I will say, hey, for this word, how similar or how useful is it to that second word? So I have a query. So I take my word, I embed it in such a way that it becomes a query. And in the simple case, you could say it's just identity matrix if it's too confusing for you. But in practice, I'm going to project it in the space, in such a way that I can nicely compare with the other words, and I'm going to project it. So I'm project my word in the space such that all of the keys are going to be nicely comparable to that query. And then I do similarity. Okay, I do similarity, and then once I do the similarity with each of them, that gives me my alpha. Okay, that this alpha here, this alpha tells me how my query, how similar, how related is it to that key. And it should be high, huh? If you remember, because you should be by yourself, you should be relevant to yourself usually. But the second one says, hey, how relevant is it to the word do? How useful and relevant? And there, maybe not as high, but as we'll see later, when we start looking at it for the do and the not, then we'll see. But that's what this alpha is, says how relevant or related. And then this attention comes from the not, and then taking the queries together, and that gives you the alpha. This is the key of transformer self-attention. And I will call this process of taking an input, projecting it in a space in such a way that I project the other one and I compare it. This is a similarity function. This is a similarity function. And I say similarity function, one thing that should come to mind is kernel. Okay? Kernel are also great as a way to similarity. So I'm making a link. Don't overthink it. If kernel doesn't ring a bell, but I'm saying kernel in the sense of SVM, not in convolution kernel, but says in SVM. But yeah, what this is going to say is say, I want to know how relevant I is to the word not. And the way I do it is I will project not and project I in such a way that they're in two spaces, but the two spaces I've been learned in such a way that I can nicely use a similarity, and they use a multiplication in the transformer for simplicity. And then that gives me how similar or relevant they are. And then that's what's called scale dot product attention. It's just projecting both of them and then just doing the dot product. That gives me the attention. As you remember, this is a vector, this is a vector, this is a vector, but I do the dot product, then I get the scalar value, okay? And so I repeat this also again for the word I do, and then it's really interesting if you remember, because do and I, probably, again, maybe not as, but do and not, when I project them, they should be projected in such a way that they realize that they are important, and that is an attention that I want higher, because that that's something that's going to be important. Because when I do the summation here, I'm going to sum over this attention and the value, this attention and the value, this attention and value. And so I want to, when I sum it here, to be sure the attention is high. And so you do it for all words, and I'm just going to show it like in a more compact way. So where I do it for all queries, I compare for that queries with all keys. That gives me all of these attention. Now I take for that query, and I'll go it for all keys. That gives me this attention. And then I do it for queries, and then I get also my values. Usually the key and the value are the same. In almost all architecture I've seen, key and values in the same. The query is really like telling what is important, what is it is similar. That's what I want to encode, is the query in this case. So I could say the keys are kind of the context, like, and the query is what I'm trying to encode. So I'm trying to encode I, but I would like to contextualize it with the key and the value. I would like to contextualize it. That's kind of the other intuition. So this is the idea of transformer self-attention. The idea here is to expand, and what's really nice is now the attention, I am expanding the concept of attention so that every part of the sentence is contextualized with all the other part of the content of the sentence. So it's almost as if any part of the image was contextualized by all the other part of the other image. That's the computer vision equivalent of that. And we'll talk about extensions from multimodal. So that's called a transformer self-attention module. And the idea here is that I'm going to use all of the input. And why it's called self-attention? Because I'm going to compare it to another type of attention soon. But here is self-attention because both query, key, and values are all coming from the same type of inputs. That's the reason for that. So what happens if we want to attend to simultaneously to multiple subspace? Okay, right now, maybe I do not like it. Maybe there is a self-attention. There's a way of contextualizing my sentence that is just about looking about negation, let's say. That could be. And then you could imagine that there's another type of interesting relationship in language which will be maybe co-reference, like it. And maybe the it refers to something earlier in the sentence, like not in that exact sentence, but refer in something longer, like if the sentence was longer. So like maybe, so maybe you will hope that your one transformer will be able to find every possible way that the words could be contextualized with each other. Let's say lexical disambiguity could be one, like plant. But it's possible that you want also maybe your transformer, your self-attention, to have one dedicated to a specific task, let's say co-reference resolution, another one for negation, another one for like lexical ambiguity. And so in the case when the transformer was proposed, they also used the idea that was previously suggested, but they applied it of multi-head. They gave this nice name of multi-head self-attention. And the intuition is simple, is now I don't have only one way to contextualize my word. So I will contextualize my word I, maybe by looking at negation, and that's the one way I will contextualize. Or I could contextualize I by looking at disambiguating lexical disambiguation or co-reference. Now, I'm giving you this example of why you would want many transformers. In practice, you let the model learn it. Although you could imagine adding this extra knowledge, I don't know if it has been done, to force the transformer to look a specific type of contextualization. But in practice, in many cases, they will just let the transformers, by having 3 of them, they will let the transformers hoping that they learn something different. And then at the end, they just have a simple linear projection to get one embedding, because at the end of the day, even if you have multiple heads, you still want to have only one embedding. And that one embedding will maybe look at all of the contextualization and learn a way to either it's an average or it could be a little bit more complex than that. So this is a transformer multi-head self-attention. Let it, yeah, so that's a lot. This is a lot, but this is very powerful. So, and at the end of the lecture, I'm happy to answer any question and go in details on any of that. But the key aspect of that is that I'm contextualize each word based on all the other words, and that's self-attention because the whole sentence is used both as a query and as a contextualization, which is the key and the value. So So it's self-attention in that sense, and it's multiple head because I may have more than one way I want to contextualize. So these W, which are looking at finding similarity, these W's, the W, Q, and K are the most important. And why are they so important is that they are projecting me in a space. So these here, I'm projecting me in a space, maybe in a space which only look at negation and is gonna bring together words that need to be negated. And maybe this one is gonna project me in a space in such a way that it looks at a co-reference resolution. And this one may project in a space that will also look maybe at only lexical. So these are very important projection, and having different one can be very useful. And then I want to ask you this question. Think about it for a second. I look at the architecture or remember the architecture of the transformer. What happens if I change the ordering of the sentence? Not like it do. So this H1 not, how different will it be? And I'm switching slide when I was this. Okay, how different that H3 when this was that ordering? How different is it when I put in this order? In the current version that I showed you, they will be exactly the same. Exactly. Okay, if you randomly initialize everything like to be equivalent, like they should be exactly the same. Okay, right now, the ordering of the sentence. So although it's really cool, huh? I contextualize based on a word, but unfortunately I ended up doing it at a big price, which is it's the equivalent of a bag of words. It's like the ordering is no important anymore. But you probably expect there's a solution for that. Otherwise, I would not ask you. Or maybe I would, but it would be an interesting research question. And so there is an idea, and that's one way to do it. And I think it's still, there's still research to be done on really what is the right way to solve that. But one way is to encode the position. So I have not like it do not. Look, well, it's even hard to say. And so I could imagine was the simplest one is to in fact encode as a one-hot encoding each of them. So I take each of my words and I know what the original ordering is. In fact, right now I show them in a different order, but in reality, what I will end up doing is keep the same order I had. I do not like it, but then but because the algorithm will not know that I was the first one, I keep it as a one-hot encoding this, and the it was the last one, so it's the last one there. So that's one simple approach. There's a small extension to that I could do, which I take this one-hot encoding and I just project an embedding, and I just a linear projection of that one-hot encoding. And then there is this question, what's your feature? What is now your feature for the word not? And then one idea maybe to sum, although I will say between you and me, it's not my favorite, or you concatenate. That feels more intuitive to me. Summing is possible, but that means that this WP will need to be projected in a space that's still quite relevant to that X here, the original word. So that makes it more challenging. Although it turned out in reality, in practice, it seems to work quite well, the sum. But concatenated seemed a little bit more intuitive. And these are just the basic. I on purpose, I'm not going to go in very, very complex, but you can look at these almost as kernels also, and like in the SVM sense, and you could also make it very interesting there. For example, you could decide to not concatenate them and leave them, or not summing them, or not even concatenating them, and say how similar these two are. How similar is the I with the not? You could say, hey, how are the words? And separately say, whoops, sorry, I press, by doing that, I press my clicker, and say separately how the position is similar. That will be another way to do this. So, but now I have my transformer. So the transformer takes my original input X, adds to it a position embedding, add it for each of them, and then the rest is the same. You go, so you take my input and I put a position embedding, and then I simply, after that, that's the same transformer. And now, if I swap the order, that will matter. What it means swapping the order is like, and it's a little bit maybe confusing, but if I change the order, I do not like it, the position is the same. So whatever word I put here, the P1 is always the P1. It doesn't change. I can put any words, it's always going to be P1. And so X1, if I put a different words here, it would be different, but the position embedding will stay the same. And just in vector format for people, this is a vector format, and I'm going to use that vector format later on. I say vector, it's in fact, to be true, it's a matrix format, because like this is a vector of vectors. So X is a vector, and for each of the words or elements in the sequence, I also have a vector. So a matrix format will be, and so the self-attention, if you remember, is we have the same input. So for the query, this is the thing we want to encode, and the context for it is the value as well. So in this case, I want to give the sequence to sequence. So now I told you how do I embedding. So now you should be able to take this idea, or maybe not able to train it, because that's going to be in a few more slides. But now you should be able to, at least if it's already trained, you should be able to take any sentence and embed it and encode it with this transformer. But I want to go, before we go into the training, which gets a little bit tricky if we want to do it in an unsupervised way, I want to ask you, like, how can I use this idea of transformer to do a sequence to sequence? Like, let's say I have one language and I want to be able to generate another language, or in a multimodal sense, you may have an image and generate a sentence, like image captioning. So for the input here, it's easy. It's a self-attention. That's I do not like it. I can use that self-attention that I told you about, and I can simply use it and take it to be able to project all of these words and contextualize them. So this is the self-attention. But how can I use something similar here? Je n'aime pas ça. Let's say for now that so if you remember, the generative models, what they are, okay? What do they have as input? What do they have, these decoders? These decoders, they often have like the word start, the token start at beginning. It goes through something, which we'll describe in a second, and then you get one token, and then you get that new word, and then you project into something, and then you get the next word. And so it's an iterative process. So let's say, and so right now, let's say that I'm right here. I already processed 3 tokens, and I want to predict that, like that third one. one thing you could do, a simple extension of self-attention will be called a mask self-attention. And the idea is really simple, is that I don't see these. So it's the same architecture inside it, is just that to embed this one, I can only contextualize with these. And to embed this one, I can only contextualize with these. And to contextualize this one, I can only use this one. Okay, so that's mask self-attention. But now the more interesting is how should we connect? Like how do I get here? Because the self-attention up to now, the self-attention needed this input the same, like here self-attention, like it's the query and the key and the values are all the same. And so here I want to use a transformer. But now it's not going to be a self-attention transformer. That's really interesting. I want to encode N. I want to take this. I want to make it in such a way that it is contextualized on also the sentence. And so how should we connect the encoder and the self-attention transformer? And I would love to make you vote on this. But the idea here is that I told you the query is what you encode, and really what I'm encoding in a typical LSTM, it's that. It's like this is the input usually that I'm using to be able to get my encoded version. So this is the query. That should always, query is what do you want to encode, and then the key and value are your context. Is like how can I use I do not to be able to be able to encode it. Another way, so I give you the intuition of query is what you encode, and the key and value is what you your context. Another way to say it is to say query is what you want to be encoded. But here the challenge is to encode it. I cannot even use my input. That's the funny part. Is it not funny? So now in the self-attention, the key and values were coming from the same sentence. So, but here what's really interesting is the only way I can re-encode star, J, and N, the only way I can re-encode it is using some information here. And that's really interesting. So what it means, it says, I'm forcing you to use English to be able to produce some French, and I want it this way, star je ne, and like I want it this way. This is what I want, star je ne, and so that's what I want. But the only thing I have as a building block is my key and value. My specifically my value is what I can build from. And so that's the interesting aspect of a transformer attention compared to the self-attention. Self-attention was a little bit easier because I can always build with myself. Like when I encoded I could always build with I as a starting, and the others were really there just to contextualizing my I. But when I use a similar architecture and I don't use it in a self-attention way, then it's a much harder problem for the transformer for the attention, because now my query, that's what I want to encode, but the only source or a piece of information or any kind of building block I can use, building materials I have used, is from another source. So this is the very interesting, and you can see, imagine if it was an image here. That would be really interesting, because now I want to produce a sentence. That's what my query is. I want to produce some words. That's what I want to produce. But the only thing I can build it from is from information that I have in my visual. So that's really interesting. So what you will get is hopefully, and we'll talk about the multimodal in a second, but I just want to give you that attention. So this is called an encoder, at least that's how they call in the original paper, an encoder decoder transformer. This will be called an encoder transformer, and this will be called a decoder transformer. This is just how they call it in that paper. I personally prefer calling it a self-attention module or transformer, a mask self-attention, and that I would personally call it a transformer attention. It's not self-attention. That's how I prefer to call them. But let's start to think about the multimodal way, because I already kind of given you kind of a hint about it. So how do you do it in a multimodal way? So now the task, and try to think about it, the task is I have language, like I really like it this time. I really like it this time. I have visual, I have acoustic. And so my goal is to encode language, encode visual, and encode acoustic in such a way that the acoustic is contextualized by the language and the vision, that the visual is contextual, acoustic, and language is contextualized by visual and acoustic. So based on what you know up to now, what will be the 101, like that you could, from the self-attention and transformer and attention and all of these that you just learned about in the previous, I don't know, 30 slides or something, how would you do this? So the simplest way is to just make it a transformer self-attention. And that takes a little bit of time to understand, because it's a little bit weird to put together all of the same in one unique transformer everything. But what it means, what will be the input in this case? Let's say I have 6 words. Let's say I have 5 frames. And let's say that acoustic, I'm looking at acoustic frame or acoustic observation. Let's say I have 10 of them. I have 10, 5, and 6. So how is the transformer? It's going to be just the sum of it. So it's going to be 21. So you're going to have a vector of 21, very, very long vector of 21. And then you will just do training of a self-attention. I didn't tell you yet how to train it, but let's say you know how to train it, or let's say it's already trained and you want to contextualize it. And then what you will do is take those 6 observations. Maybe you have a vector for each of them, and then say maybe from word to vec or something. And then you have from CNN, you encoded each of them. So you have 5 vectors. And here you have it maybe through your spectrogram or some other, and you have a vector. Or you use some acoustic features like MFCC. And so you have those 21 features, and then you will simply run through your transformer, and then you will take the last 10 and you will call it my embedding of acoustic. You're going to take the first 6, make it the embeddings for your language, and 5 for your visual. So that's a simple. Now you have to ask yourself, what if I change the ordering of the visual, language, and acoustic? Will it know it? Will it know? Like you have 21. If I reshuffle them. Now, for the language, I have a position embedding. I could imagine position embedding also here using the same way. So order 1, 2, 3, 4, and 5, and the same thing for acoustic. But how is it between modality? How do I do it? Position embedding. You can just create a modality embedding, a one-hot modality embedding, 0, 1, like a 3 length 3 vector. So 0, 0, 1, 0, 1, 0, 1, 0, 0 to encode the different modality, and still have maybe a linear projection, like to project these one hot into something that will be closer in that space to the embeddings of each of the modality. But that's one way you could encode that, and that's in fact used effectively in some cases. So self-attention is one way to extend the idea of modeling this. Can you think of any other approaches? And one view is to do what I would call cross-modal transformer. And the idea is, the intuition is to encode language. I will say, let me encode language contextualized based on vision. Like, what is vision giving me that was not already in language? And then similarly, I will say, like, what is it in acoustic that could help me with language? So instead of having one transformer and all do at the same time, I'm going to do it in a bimodal way at the same time, and in a directional way, which is even more important. So it's not just going to be a self-attention with visual and language. So that would be the bimodal. So you could imagine a version of bimodal self-transformer attention, which takes language and acoustic together, have a self-attention transformer, get embedding for H and A, and then do the same from language and vision, get a H and a V, and take my H and a V and just maybe a linear projection. That would be kind of a bimodal transformer self-attention. Here they do a step further, which is a cross-modal transformer. And that's not going to be a self-attention. What they do in this cross-modal transformer or cross-modal attention, transformer attention, is that one modality will be the query. That's what I want to encode, language. But I'm going to use, the only thing I can use it for is going to be that other modality. And so I take my language and I'm going to say, hey, in vision, is there anything in vision that can use, could make it so that you can recreate alpha? And that's what it will give me here. With the output of this will be the best I can recreate from just using vision. And the key aspect after that is a residual node, which will say, hey, what is different between this and this? What is different? And whatever is different, add it to me. And that I don't show it here, but that's what is done here, is like it says, whatever is different from like what you like, this is vision, and that's what you could get from it. But now I'm going to say, okay, add it to me. We'll have a residual connection here. And the residual connection is really important because then it will say, hey, from language, what can I add to it? So I didn't put it here, but there will be also a residual connection to allow me. So I will say vision and language, and then what you add to it to the language. So language pre-training, token level and sentence level. And I want, sorry, I just, yeah, I want to language. Yeah, I think I got it correct. Yeah. Okay. Alpha to the beta. Yeah. Okay. Yes. So language. So, but how do you train this? And how do you take and train this in an unsupervised way, hopefully, and then we can look at fine-tuning it eventually. So I do not like it. I do not like it. And so I want to train to be able to generate new embeddings. And so I would like to train it in a supervised way. You probably have the intuition that we will use something similar to the distributional hypothesis. Distributional hypothesis says the meaning of a word can be approximated by the meaning of the other words. So that's probably an intuition. But I want to be able to train my model in such a way to get these embeddings. Oh, I may also want to train my model in such a way that I get only one embedding for the whole sentence, instead of having to maybe have a, I don't know, an RNN on top of this, or doing a pooling, like a mean pooling on top of that. I'd like to have upfront a language that. And so, and in practice, I will often like pre-train and maybe on a very large corpus of unlabeled data of maybe a word, and then I will fine-tune it to my task. So I will fine-tune it to my task. This could be very simple. I could fine-tune two ways. Usually you fine-tune. So one way is to fine-tune by adding another layer on top, and then whatever you use here, you learn in a general sense, and then you add a few layers. Or maybe what will be even nicer if I could also fine-tune the inside of it, like fine-tune that as well. So that's my goal. And so one very interesting way of training those transformers is called BERT, bidirectional encoder representation from transformer. And here the idea is there are quite a few advantages of that approach. One is to jointly learn representation for token level and sentence level. So in one model, I'm going to learn how to encode at the sentence level and also encode each individual token. So that's will be something, I mean, maybe yes, sometime I would like to use only one and not the other, and maybe there's a slight waste there. But the nice thing is the same model will give me both. There is also design this so that the fine-tuning of the will be done with the same model. That's a small thing, but it's an interesting thing. And then one thing that I personally like, they don't people emphasize as much, but this architecture can be extended really easy to get a large corpus, or also get a difference between sentence, because there are tasks where I have a sentence or I have a corpus of sentence, and I just want to get the embedding for each words in the sentence, or I want an embedding for the whole corpus, or like the whole sentence. But there's quite a few cases where I want to compare something together. I want to compare two sentences, like I have a question and an answer, and are they the same? Or two sentences, are they similar? A question and answer, are they related? So this is very interesting to have the same way of learning that will allow me to get also prediction of the joint embedding, one sentence embedding, and if I needed, the same model may be able to do some kind of more relative or differential task. And this is all done in a long-range dependency and bidirectional. So that's the advantage, but that is the advantage of the transformer. So that one is on. So how do we do all of this together? All of this. So what is going to be here? The model. It is a transformer self-attention. But there's a small change. Is now we will add a special character. In fact, two of them. One as the start of the sentence, or like just and then another one as a separators. But that's the only two difference on the input. But how do we train this unsupervised? And so there's quite a lot of extension of how this could be trained. I'm going to share one strategy of how to train this. And the first one is the distributional hypothesis idea. And the distributional hypothesis idea is that if I mask a word, I should still be able to embed it, even if I don't observe it, because I have my context into there to help me. So so in this case, like so what will be the loss in this case if I was to just use this is just how well. So all of these, for this exact sample, the loss will only be defined on these tokens that were masked, and that will be my loss. So the loss here will just be defined on these masked cases, okay? And so how close am I, if this is an embedding, how close that word embedding is to the real ground truth word embedding. That could be one way. Or if it's a one-hot or different version. Now, what the other thing that's interesting is how do you train to get that sentence level embedding? And there are many possible ways, but one way to get an embedding to know if this one is to get we want a loss that will allow you in an unsupervised way get one embedding for the whole sentence. And the one idea that was proposed was is this sentence the next or not, if this sentence the next or not to this sentence. And so this HS will be there and used to like simply detect is it yes or no. And that's one interesting loss. And so the loss in this case is only at this point. Is it the next or not? And you have the ground truth because you have a large corpus with sequence of sentences, and you can simply there. And the training data, that's the corpus. And then what's really interesting also is that you can start also look at how do you differentiate between different sentences. How does because you have to ask yourself to train this, it has to know that this token is from one sentence and this token is from another sentence. And the normal position embedding will just say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So by default, the position embedding will not, the typical one will not tell you that this is a different sentence than this one. So you can imagine there's a nice simple way, which is just a sentence embedding or segment embedding. So really the input to each of those tokens will be the sentence embedding, which could be just a one-hot. Is it the first sentence, 0 or 1? Like, and there's just a linear projection maybe on top of that. That's what will be this. And then the typical position embedding, you could make it sequential, or you could have restarted here. That would be another way. Maybe you could have done it. And then you have the embedding of each word. And that's what you can sum them. That's what they did in the original paper, or you can just concatenate them or do some other way. So this is the way to train the BERT, and then you can use it for different tasks. So you take that has been trained with these two loss functions, and it can be trained in an unsupervised way. And then now you can use it. And now if I ask you a task, and I want a task like sentiment analysis or document classification, how can I fine-tune this? It's simple. You just use this part of the transformer. So you put as input CLS just because that's the token that the transformer knows about, and then you encode your input, and then I am going to ignore all of these and just take this sentence level embedding and just learn, I don't know, softmax or something on top of that. In fact, what you could do is fine-tune only this part, but what they found in practice is that the fine-tuning of this is really, really efficient, very efficient. I mean, give the best performance. And so they will, in fact, only put the softmax here, no linear projection, nothing other than the softmax. And then all the fine-tuning will be here. And what are my weights in this? You have WQ projecting your query, WK projecting your key, and W. So although it looks like a big and complex one, there's only those 3 projection matrices, and the rest, there's a lot of computation, but the number of parameters are not small. I will not have small. It's quite big because you can do it for many different words and all this. But I will tell you why it's big. If all the sentences you had were always really short, it will be very easy. But the basic transformer requires to know the length, the maximum length of your sentence up front. Now, there's been extension, XLNets and others, to make it almost like a sliding window kind of thing that will allow you to handle that. But the default one will kind of almost have a predefined length of this. And that's a little bit why the big number of parameters. But in general, there's only 3 matrices for each layer that is to train. So that's what you will need to fine tune here. If we have a label for each token, let's say that we have sentiment for each token, then I can nicely have maybe just a simple projection, linear projection here for each of them, just to project my embedding into my whatever label I have here. And then fine tune this as well. And by the way, do you end up having a different weight for CLS? Like W, you remember there's a W for query, W for key, or W for value. Is it different, this W for CLS, than it is for the other words? No, it's not. Okay, so it's not. It's exactly the same W that is used here to embed HS. It's the same W. It's just that the model has learned and it has tweaked the W to respond. So specifically the W query probably is going to be very important in how it embeds the CLS so that it takes it and embed for the HS. So, but it's the same W set of parameters for all of them. And then you ask yourself, another task we could do is how to compare 2 sentences. Because it was trained in this way unsupervised, it knows what a separator can be used. And so by simply adding that, it should be giving you an embedding. If you didn't have it, that separator, then that embedding will be just a sentence. But with it has the separator, it has learned. So if you wanted to compare 2 sentences, like natural language inference, that would be an example of that. So I do not like it. It's quite different from I enjoy my time here. And so you can do, and then you can even use the BERT, which is really cool, from a question answering. And so question answering, how old is the man? And then you would like to generate, he is 25 years old. That's what you would like to generate. And so sorry, I should probably have put them here and really have the token start here. Have the token start and have everything shifted. But yeah, so the way to do this will be that you want to input the question and you want to be able to generate an answer. And so how do you do this? You will, in fact, in practice, only one way to do it, let's say question answering, you want to, and this is, sorry, I know, I was correct. I was correct in my slide. I apologize for that. Let me, I was trying to answer a different question. Here, the task, sorry, is not question answering like writing the question, writing the answer, but the question answering is like, I have a very, very long text. I have very, very long text here. I have extremely long text here. And the idea is that you want to be able to find which part of this text, which part of the text is the answer. And so in this case, then I will use, I can use a nice softmax. What it does, it looks at all the text and say, where is any of them the start? That's comparing the start token with each of them. And you can, and then see when there is a max value. So is this looking like a start? Is this looking like a start? Is this looking like a start? So that's my query. Like my query is going to be this in a sense. Look, and then I will use also context. But the H is not just the embedding of the word, but it also contextualized on the questions. So it's context is the embedding of the word contextualized on the question, and that will give me a nice. And you can do the same for the end time, and this is done from fine tuning. Okay, the last part, I have 3 more slides, is how do you do other extension, and you will have some of it in your reading, and I invite you to look at follow-up papers that been in that topic. There's a lot of interest there. But the idea of multimodal, how do you do with multiple modality? What if it's not just email like language, but I also have an image? Like I have maybe, let's say I have unsupervised data, which is not really unsupervised, but it's paired data. I have this paired data between captions and images, and I would like to learn a nice embedding. The simple way is to just concatenate everything and make it as a self-attention. That will be one way, like a self-attention. But how do you train it? Then you can do the same idea as distributional hypothesis, and you mask certain word, and in that case, that gives you the loss. Or you can also mask or zero out part of the image, and also try to see how well you can either regenerate or extrapolate it. So can you, from this part, be able to regenerate this part, for example? A lot of it will be done at the object level, so they will not take the whole image and just randomly slice it, but instead they may just do it at the word level. Another way that builds a little bit from that intuition I talk about, I think in Fusion, I believe I talk about it, is that sometimes you have one modality that is stronger than the others. So language may be stronger or more relevant, not stronger, but more relevant to the task. And so in that case, you could embed your word in such a way that the word is the most important, but you're kind of contextualizing acoustic and visual, and then after that do the multimodal self-attention like a BERT. But as a pre-step, it just does the so it's one other way to do the embedding as well. So I'll let you read other ideas on these multimodal transformers. I think one of them is for dialogue that we suggested, and I think was visual BERT, and some of them are also optional. So thank you very much for your attention.